Okay, I welcome you all, and in continuation to our discussion on the postulates of quantum mechanics, today I'm going to talk about a story. I think everybody in this classroom must have seen the Goldilocks and the Three Bears. Anyone among you? Have you seen that? We have books where you have those stories written on Goldilocks. Let me remind you about this story. There happens to have a girl, and she moves out of her house, and she is lost. She doesn't know the way back to her house, and she is very horrified. She's very feeling complicated. There is a huge mesh of jungle around her. And she keeps on walking, and she keeps on crying as well. And she finds a house. And this house belongs to three bears. You remember? You have a papa bear, you have a mama bear, and then there is a baby bear. And when she goes close to the house, she knocks the door. There is no response because there are no bears inside. And she opens the door. And when she opens the door, she finds porridge. She finds 3 bowls filled with porridge. And you can understand 3: Papa bear, a mama bear, and the baby bear. And one she finds extremely hot, another she finds extremely cold, and the third one she finds right. And she chooses the one that's perfectly right. She eats the porridge, she moves on in a corridor, she finds there are 3 chairs. And she sits on one chair, she finds it very hard. She sits on another chair, she finds it extremely soft, and she sits on the third chair, she finds it just right. And finally, she goes into the bedroom. There are 3 beds. She finds one of the bed is hard, another bed is extremely soft, the third one is just right. This is the story of the Goldilocks. But we have been floating this story in quantum mechanics, and we talk about the quantum Goldilocks effect. So what you observe that, see, if I talk about plants, all of us have understood at least this part of science in our 10th class, that what is photosynthesis, right? So what is it? It's about light falling on the plants. Now the point is, it was discovered in 2010 that the interaction between the sun and the cells of the plants, this interaction has to be just right. The nature allows this interaction to be quantum mechanically just right. What does it mean? It means if I have a system A, I have system B, there is a lot of randomness in system A, there is a lot of randomness in system B. If they will interact, they will not make sense. They will not transfer maximum information. They will not transfer maximum energy. Now, if the 2 systems, A and B, A is very sleepy, B is very sleepy, they will not at all interact with each other. So there is no transformation of energy and information. But if the 2 A and B systems are oscillating, the randomness that they have, if they have just beautiful randomness, so that A can transfer the maximum energy to B, and B can transfer the maximum energy to A. This is what is happening in plants. It is just that kind of compromise between the cells of the plant and the solar energy. If there is no cohesion like this, if there is no compromise like this, then this much of energy cannot be transferred. This is called coherence in quantum mechanics. Nature is playing with it. Nature is doing it every day, but we fail to do it in building a quantum computer. See, nature is doing it around us. It's happening. You have the plants outside. This is happening. And we are trying to build a quantum computer. And the problem is decoherence. We are in search of that coherence that is practiced by the nature. So this just right is what is called as quantum Goldilocks effect. Got this? So I wanted to just fascinate you with this argument, because when you write down the equations, it becomes crazy at that time. So I wanted to give you an insight about that. And you can see from this photograph, you can sense it, that you have too hot, too cold, and just right. So nature is making it just right. You know what does this just right mean? It means 100% transfer of energy. The plants are transferring 100% energy. There's no loss of energy when it comes to sun and the cells. So in nature, what we have situations like where we have too much of noise. Now think about, suppose there is a hurricane and I go outside and cry. Would anybody listen it? It will not make sense, because there is a hell of randomness, right? So this just right is making sense in quantum physics. And too little noise, that means A is not interested to interact with B. Vacuum can be taken as an example. And just right balance. It is the quantum plus the cooperation between the environment. So this is it. Okay, if you have any queries, you can tell me if you have anything. So we have to proceed on. I would like to shut it down. How will I get my, I should close the cost. Where is it? Yeah, come in. You're late. Okay. So now we'll be talking about, again talking about the postulates. But we will try to go to the ground level now, because we started something purely Dirac-based, purely Hilbert-based. Now what we have a wave function. Okay? So we have what we have is, you can represent your system by a vector known as wave function. So we want to focus on this now. And this wave function can be represented as psi as the function of position and time. This wave function is carrying the whole information about the system, but this wave function has no physicality at all. And what makes it physically applicable is Born interpretation. Born interpretation, isn't it? So when you talk about the Born interpretation, that tells us that you can calculate the probability density, right? So if you multiply the complex conjugate of this wave function with the wave function, and you multiply it with some volume, say dV, this will provide us probability density, right? But the point is the location. where the particle is. So your system can be an ideal system, say particle in a box. The universe can be treated as a system. So in doing so, what we write down this as an integral from minus infinity to infinity, psi star of xt and psi of xt, and if I think in terms of only one dimension, I'll write dx here. So I'm moving from the volume to one dimension. Now, what does this mean? What do we call this? This wave function must be square integrable. And the value of this integral over the limits from minus infinity to infinity is equal to 1. Right? So what we have? We have an integral like this, minus infinity to infinity. You can write psi of x and t mod square dx is equal to 1. So this equation is telling us that this wave function that we have, what we call as, what we consider as the postulate 1, that your system can be represented by a wave function psi, it must be square integrable. It must be a square integrable function. And the other things, like this wave function that we have, it should be single valued, right? It should be continuous. It should be square integrable. Its derivative should be continuous, right? And it should perish at infinity. So these are some of the important arguments that makes this psi of x and t as wave function. Look. Okay, that should be clear. Okay, see, we can have an example. Say, for example, I choose a graph like this, and suppose I show something like this. This is psi, and let this be x. What do you think about this graph? Is it acceptable? It is not acceptable because if this graph is going to infinity, but it is acceptable if you will limit it. Right? Getting my point? Okay? So you can have another situation. Suppose I have a curve like this. Okay, so this is representing psi of x, and this is x. Now what about this graph? Is it acceptable wave function? Are you saying yes? How? There is limit, no problem. Okay, this is point A and this is point B. Yeah, come on. Come on. Yes. Is it an acceptable wave function? Yeah. No, it's not. Why? Do you remember that when we imagine electric lines of force, what we say, two electric lines of force cannot intersect. And how do we explain that? We explain that using a tangent. We draw the two tangents and we say, come on, at this point you must have two directions. But you cannot have two directions of electric field at one point. And the same is the case with this. Here you have psi, you have psi, you have psi. So here you have probability of finding, probability of finding, probability of finding. So at the same point you cannot have three probabilities. Right? Therefore, this graph is not acceptable. Got my point? So this is how we can treat it. And you know the other things you do then, that which are acceptable and which are not acceptable. Okay, now let's move a little bit. Now say for example, I have an operator. Say I choose an operator A And this operator is d by dx, right? And I choose a function. I have chosen an operator. Now I'll choose a function, say f. I'll call it f of x. And this f of x is, I will choose it as, say, sine x. Then I'll choose it as, say, for example, 3x. I'll choose it f of x equals e to the power of alpha x. Okay? Right? So what I have an operator d by dx, and I have the function sine of x, 3 of x, e to the power of alpha x. Now let me go with the first one. Now what I'll do is I will operate my operator on my function. Right? So I will write a cap f of x. Now what is a cap? It's d by dx. Okay, I should not put it. So what is f of x? It's sine x. So what I'll get cos x. Right? Okay. Now the same thing. D by dx of 3x. That will give me 3. Right? So here you have a function. Here you have a function. Again, I will use d by dx e raised power alpha x. This will give me alpha e raised power alpha x. Right? Now this is your function. This is your function. You have sine x, you got cos x. It's a function. 3x, it's a function. You differentiated it, you got 3. But here, you have an eigenfunction. Because you are making use of your operator on the function, and you are getting back your function. See, here you're not getting your function back. Here you're not getting your function back. But here, you are getting your function back. So, I will call this e to the power of alpha x. What is it? E to the power of alpha x is an eigenfunction. Are you getting it? Right? And alpha is your eigenvalue. Right? So all functions are not eigenfunctions. Right? So you have special functions which act as eigenfunctions, because when an operator acts on these functions, you get back your eigenfunction. You get back your function. That's what we call as eigenfunction. Is this clear? Okay. Now let's talk about the commutator. Okay. Now, if I choose an operator, say for example, I choose an operator a cap, and this operator I choose as the position operator, x. No, I shouldn't do it. Let me choose just one operator, x. Oh no. I want to obtain the commutator relation. So I want to put the operator A. I want to put the operator B. And I want to put a function, say f of x. Right? And what I'll do, I will keep A as x cap operator. And I'll keep B as d by dx operator. And I'll keep this function f of x as sine x. Clear? Right? So what I have an operator A. I represent it by a position operator. And then I have B. I represent it as d by dx. And then I have f of x. I represent this as sine of x. Now what do you get out of it? If I act like this, a gap, b gap, f of x. Yeah. So this will be, yeah. You will first act your b on f of x. So what will happen? X. No, I'm not able to demonstrate it that way. What you are getting? So b f of x will give us cos of x, and operator x will give us x. So x cos x. Right? So this will be x cos x. Now, if I reverse it, now if I go with b and a, so you will have d by dx first, and then you will have x and sine x. Are you getting? Because I'm just looking for the order. In the first case, I'm taking a, b, I'm acting b on the function, then a. Now I'm acting a on the function, then b. So you are left with d by dx of x sine x. So obviously here you will have a UV rule. So you will have x cos x plus sine x. So you can clearly see the anti-commutation, right? So you can clearly see that a and b is not giving us b and a. And in most of the cases in quantum mechanics, we have non-commuting operators, right? Let's go back to the eigenfunction. Now we understand what eigenfunction is. And I think previously we noted down the momentum operator. We noted down the energy operator. Could you tell me about that operator? The momentum operator? Yeah. So for momentum operator, taking it along x only, okay? It is p cap, okay? What is this? This is minus IH bar. I will write d by dx, okay? And I'm exclusively using it along x, isn't it? Agreeing? Okay? So now I would like to multiply this by the wave function, right? So what will I get? I'll get p psi equals minus IH bar d psi by dx, right? We have already seen where from this operator comes. We have done that. So what can I do? In the left hand side I have p psi. I'll keep psi there. No, I'll not keep it there. I'll keep, come on. Come on, tell me about the equation, yeah? So d psi, I'll keep there, I'll bring psi down. So I'll have d psi by psi. Okay, take everything on the right hand side. Come on, what you'll get? It's 1 by minus IH bar, yeah? And then p and dx. You check it, right? Okay. Now the equation demands integration. Okay, so I can integrate it. So I'll take log of psi equals, was it minus? But you'll take this iota up, it will become plus. So this is iota p by h cross. Yeah, here differential and integral will cancel. So here you will have x, and then you will have a constant of integration. Let me choose that as log of a, right? You're integrating it because this is indefinite integration on both sides. So I'm introducing a constant over here. Are you getting it? So what I'll have log of psi minus log of A equals I P by H bar X. Now this is log m minus log n, so this will lead us to log psi by A equals I P by H bar X. Right? And you can transfer the log and you will have an exponential on the other side. So what you will have is you will have psi equals A e to the power of I P of X divided by H bar. Right? What is it? It's an eigenfunction. This is a function. Right? So psi equals A e to the power of I P X by H bar. Now see, what I want to demonstrate at this point is this P that we have in the exponential. Can this P be a complex number? Can this P be a complex number? Now see, if P is a complex, that means it has iota with it, right? So what's going to happen? So it has iota, that iota will be cancelled by this iota. So what you will get? You will get an exponential function without any limit. Are you getting it? Are you getting it? So this P that I have, this P cannot be a complex number. Again, I'm telling you, if it is a complex number, it's going to neutralize this iota. You will have an open exponential function, and this exponential function will have no physicality. But, so what does it tell me? It tells me that P has to be the real one. It has to be the real one. Now, what does that mean mathematically? Will it make sense? Will it make sense if P is real? And this P will come as your eigenvalue. Yes. If this P is real, what you will have? You will have e to the power of I theta. This is what you will have, isn't it? And this is what? This is cosine theta plus iota sine theta. Now what is this? It's not something infinite. It's closed. Minus 1 to plus 1. What is this? Minus 1 to plus 1. So this is another way of understanding that the eigenvalues that we obtain, they have to be the real eigenvalues. Because they will not make sense if they are complex. Your wave function will become infinite. It will not be physically demonstrated. I think we'll stop. If you want to ask me something, you can ask me. Yes? Didn't you enjoy the story of Goldilocks? Huh? Could you sense it? So this is how quantum works. And this is what people are working on in quantum computer that's being built in IBM. They are trying to build it in a way that there is no decoherence. And this is extremely tough job that the people are doing. These great personalities are doing. So that means we can understand the greatness of the Creator. He is doing quantum mechanics with a simple process known as photosynthesis. And that too, he is doing it at the room temperature. There we are doing it at temperature that's close to liquid helium, it's nearly 4 Kelvin. We take it down to that temperature so that there is no noise, so that there is no decoherence. This is the beauty of the nature. This is how nature moves on. So with this, I would like to thank you all. I would like to stop this discussion with you.